provided that everyone can hear me if I don't. Can you hear me at the back? You can hear me. All right, please shout if I should, for any reason, lower my voice, and you can't. And this technology is here, and we'll use it. Thank you. Thanks, Francois, for your introduction, and thank you all for having me here. It's a real privilege to be invited to speak to FOTAG this morning, and especially so because our experience, that's the experience of Sue, my wife, who is here in the middle of the room, and me, our experience of Arderne is quite a recent one. It just happened by coincidence that it was during Arbor Week, the latest Arbor Week, that Sue said, we've got to go and have a look at Arderne Gardens. We've never been here. Sue is a landscaper and loves trees and has grown up with gardens. Her mother has green fingers and Sue has green fingers, and she loves beautiful gardens, and we'd never been to Arderne. Sue said, let's go and have a look at Arderne. So we did. And we were gobsmacked as we walked around those gardens, these gardens. And it was a wonderful experience. And one of the things that drew my attention was that a number of the trees had been marked as representatives of Gondwana. And now I'm a geologist, and I think there was a time when it was really only a few geologists who'd ever heard the word Gondwana. But I think these days, I'm sure all of you as members and fellows here know about Gondwana, but I think most people know about the supercontinent that gave birth to all the southern hemisphere continents plus India, and the phenomenon of plate tectonics is well understood, and so on. So I was interested and intrigued that I should see these plaques on the trees denoting their significance as Gondwana representatives. And in the end, I got hold of Joy and found out how I could learn more about the reason for the Gondwana connection, as it were. And Joy put me in touch with Hank, and Hank was good enough to walk around the gardens with me, and I think Christopher came with us. My son Christopher and his fiancée Melissa are here this morning, and we walked around the garden with Hank, and it was a singular experience. It was really wonderful. And from then onwards, from our first visit and that follow-up visit with Hank, I realized that Arderne is and I have described it in a book that I'm writing as one of Cape Town's best kept secrets. And it's a pity if it is kept as a secret. It should be much more widely known than it is. And I just would like to thank Hank and Francois and Joy and all of you for having me here this morning as your guest. And I'm very humbled by that fact that we are here entirely as your guests. But I haven't been invited to waffle about my own feelings. I'm going to tell you something. I'm a geologist, as I might not have mentioned. The talk that I'm going to give you this morning is partly geological, mostly geological, and because few, if any of you, are geologists, I hope that a lot of it will be new and interesting. And what I chose to call the talk, and which Francois has read out, and which you've seen on the notices, the invitations to the meeting, the talk centers on a book that I'm working on, the subtitle of which would be The Incredible Journeys of Birds, Trees, and Tectonic Plates. And so let's get into the talk. No. Sorry, I'm not very technologically competent, so there we go. Right, now where the story starts is, it was many years ago, many decades ago in fact, that I was in central Brazil, having seen working as an exploration geologist, having seen lots of extraordinary birds that I'd seen in pictures but had never seen in the flesh, as it were, and having satisfied myself that South American birds, Brazilian birds, were different. I was on a field trip and we had stopped to have lunch in a situation very much like that. That's a picture of the interior of central Brazil. And imagine, if you can, halfway down that slope, a bird, it's midday, in the middle of the day, it's warm, it's just the same as in the African bushveld. Not much moves in the middle of the day, everything's resting in the shade. But lo and behold, as I looked out over the slope, I saw a bird take off from a tree and fly over the canopy and land in another tree. And from its flight, I just was absolutely gobsmacked, because I thought to myself, well, if I were in Africa, I would say that was a woodpecker. And a woodpecker has a very any African woodpecker has a very characteristic flight. And this flight was just like that. And I thought, well, curious, but I'll never know. But, to my delight, the bird took off from the tree that it had landed in and flew straight up towards us and landed, 30, 50 meters away from where we were. And it wasn't long before I heard the tap, 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 tap. There was no doubt it was a woodpecker. And I thought, well, perhaps I shouldn't be as surprised as I am by this. After all, birds have been around for a long time, and they were very probably on the continent, supercontinent of Gondwana before it split up. And populations were divided. Some stayed in Africa, some moved with South America as it drifted away, and that's the explanation. Let me show you a picture of the woodpeckers that one might see in the two places. That's the Brazilian green woodpecker. I don't know that that was the bird that I saw by any means, but they're probably both quite representative of woodpeckers on the two continents. Now, the writing on the right-hand side of the right-hand picture is not very clear, but it's a good common African cardinal woodpecker. And the resemblance is striking, I think you'll agree. So, next time I was back home on leave from Brazil, I went to see a professor of ornithology at Maritzburg, which is where I was at university, and I said to him, I've seen this woodpecker in Brazil that looks like an African woodpecker, and I was puzzled by that and decided in the end that the reason for this is quite simple. As a geologist, I know about continental drift, plate tectonics. In fact, I didn't say plate tectonics because plate tectonics was not then a term in common usage. But everybody in South Africa, at any rate, knew about continental drift. So I said, surely an ancestral population of woodpeckers was divided during continental drift, and they went their own ways. The professor said, not necessarily. But he didn't give me an alternative. And he started speaking ornithology, and I didn't understand very much of that, and I politely excused myself. My head's spinning. But I was fairly determined to pursue the option of the explanation lying in continental drift. I went back to Brazil. I went back to South America, and we spent some time in Chile, and we left Chile via Paraguay. As we were driving into the Foz de Iguaçu, which is a spectacular waterfall, which is on a river that divides Paraguay, Argentina, and Brazil. And that was where we were entering Brazil from Paraguay. And we drove into the little town at the border, and we drove through an avenue of, I don't know, 5 or 10 kilometers of what I was absolutely convinced were completely African coral trees. And that is a tree called, I must apologize that a lot of my images have been taken straight from the internet, and you'll see the annotation accordingly, but they're decent enough pictures and they show what I need to show. So the trees that I saw, which I was convinced were African coral trees, looked like that. Now, that was an avenue. And I thought, well, maybe I shouldn't be too surprised by that. We plant South American trees, jacarandas, all over South Africa, Pretoria particularly, but elsewhere. So why should they not plant some of our lovely African trees? I'll show you just by way of comparison what the African tree looks like, but it's not a brilliant picture, but gives you an idea. Now, in following up, I had another string to the mystery that I had faced with the woodpeckers. I realized after a time in Chile that there were other African look-alike birds in South America, and now I discovered trees that were apparently not African trees. I found that they were South American trees, but appearing to all intents and purposes just the same as our African trees. And what had happened was that I had found myself willy-nilly entering into the field of biogeography. And it's a bit of a forbidding term, but really it just means biogeography is just the name given to the science of how living things got to where we find them. When Darwin traveled on the HMS Beagle 200 years ago, the conviction was in the early days of geology that, and biogeography, was that creatures, trees, plants, living biota of all kinds had been placed where the good Lord decided to place them. They didn't move around. Darwin soon became disabused of that notion, firstly in the Falklands and then in the Galapagos, and the work of Darwin and his famous Darwin's finches in the Galapagos is probably well known. But the understanding of biogeography, how living things got to where they are today, is that it happened in one of two ways. It happened either by what's called vicariance, which is that barriers formed which were not crossable by plant seeds and birds and creeping creatures and things, and that just the same as my original assumption of the South Atlantic dividing woodpecker populations, erythrina populations, that is vicariance, is when either a mountain range such as the Andes, which was pushed up as the South American plate rode over the Pacific plate, or an opening ocean divides the population. It's a passive process as far as the animals and plant life is concerned. They don't decide to move to a more congenial place. They just find themselves being moved or being separated by a mountain range, so that's precarious. The other option for how things got to where they are, living creatures, living things, is called long-distance dispersal. And that is something that Darwin encountered. Darwin's experience was not such a long-distance dispersal, but it was dispersal nonetheless. He saw mockingbirds in Chile, and he saw the very same, apparently, but not quite the same, very similar mockingbirds in the Galapagos. They had presumably flown there from South America, or something like that had happened. That's a long-distance dispersal. Sorry, can you all see that? Yes. Now my preferred explanation was that what I had experienced was thanks to continental drift. And the contrary words of the ornithology professor hadn't deflected me too much, partly because he hadn't given, remember this was, I should have said, this was in the late 1970s, so it's over 40 years ago. So I was inclined to arrive at the solution of the woodpecker mystery, as I've called it, to pursue the continental drift explanation. Now, let's have a quick run through the evolution of the theory, which became the principle of continental drift and plate tectonics. The first person to come up with the idea was an Austrian called Alfred Wegener, and his main thinking, and the main thinking of, in fact, I am not 100% correct in that, because Alexander von Humboldt, long before that, had the same idea. And people who have said, well, this is a jigsaw, the continents as we find them, but let's put the pieces together, and the obvious pieces to put together are Africa and South America. And that was Alfred Wegener's main thinking. It was what drew his attention to the possibility that the continents had formerly been, other than we know them today, that they'd formerly been all molded together. And he pursued that, he wrote books on it, and he is generally known today as the founder, Alfred Wegener is known as the founder of continental drift. That gives you an idea of how Pangaea, which was the name given to the two supercontinents, Gondwana in the south and Laurasia in the north, how they broke up. And it's something that probably most of us have seen. So it's nothing very new. If we're going to look at the division of an ancestral population of birds, how long have birds been around? How long have they been around for long enough to have been divided when the continents divided, split up? And so one of the first things to do was to look at the history of birds. And I think most of us know that birds were descended from dinosaurs, and that on the left is Archaeopteryx. I'm sorry the name's not very clear to see there, but it was found in Bavaria. Quite a few skeletons, fossils have been found in limestones in Bavaria, and it is generally accepted, although there's still some argument as to whether it's a dinosaur or a bird, it's generally accepted that Archaeopteryx was the first bird. And they've been able, from the number of fossils collected, to more or less construct what the bird would have looked like. On the right-hand side, you see an artist's impression of what Archaeopteryx would have looked like. Initially, it was thought that they clambered up the trees and flew down from the canopy, from the branches of the trees, but subsequently, and I don't even think it's fully accepted, but there's been a lot of evidence to show that, in fact, they could take off from the ground, provided the wind was correct and so on. So Archaeopteryx was, let's say, the first bird. That's a picture of Alex du Toit, who, as you can imagine, is a South African. He grew up in Cape Town, he went to Bishops, grew up in what was then called Kleine-Schuur, which was next to Groote-Schuur, and he is considered by all South African geologists, even the youngsters today, I hope, as the father of South African geology. He was a hugely prodigious worker, and he, like others, like Wegener and others before him, was very much attracted by the idea of the rejoining of Africa and South America, but much more than that, as a geologist, which Wegener wasn't. Wegener was a meteorologist, and they call him a geophysicist, but he was not a geologist in any event. Du Toit was a geologist, he was a field worker, he was a man who produced half of the geological maps of South Africa today, and he was absolutely intrigued by the fact that from work that others had done in other continents, there were fossils in Africa that were exactly the same as fossils in other parts of South America. There were plant fossils, animal fossils, and there was no doubt that they had all roamed some ancestral, huge supercontinent, which had already been given the name of Gondwana land, it is probably called, but that's become streamlined to Gondwana. And he was sent by the Smithsonian Institution to study the geology of South America. And he came back, and he was absolutely astonished. That's what he was that famous that he found his way onto a stamp more recently. After his trip to South America, he produced this book called Our Wandering Continents, and I should have told you that the world of geology in those days, in the first half of the 20th century, was mostly completely contemptuous of the ideas of people like Wegener and Du Toit and lots of others who were complete mavericks and heretics in the field of geology, who proposed that continents moved around the planet. How could they? And this was the problem. How could they? Nobody was able to propose a mechanism whereby continents could move around. All the evidence was there that they'd done that, but it's very much like a crime scene in which the detectives provide all the evidence, but what was the motive? Obviously there was no motive for continental drift, but there had to have been a motive force. What was the force moving the continents? Nobody could come up with the answer to that until in the late 70s, technology had developed to the point where geophysics could give some answers and give enough answers to put together a completely cohesive mechanism for how the continents had moved, which was, very simply put, was convection in the mantle, in the fluid mantle, moving the solid crust above the mantle as it has. In that book that Du Toit produced after his trip to South America, he produced this map of the geology of the two continents. He linked them up as one would, any of us would be able to put a very good fit onto the eastern coast of South America and the west coast of Africa. And we wouldn't be able to link the geology as Du Toit did, but he found time and time again, he he stood in the mountains in the so-called Sierra de la Ventana of Argentina, and he just shook his head, because he might just as well have been in the Cape Mountains. The folds were the same, the rocks were the same, and he was thousands of kilometers from Africa. But there they were. And so that was just one. He traveled around a lot of Argentina, Brazil, and places further north and west, and he came back and he put together his theory. Now we move on to more technology, where they discovered, to the astonishment of geologists around the world, that the Earth's magnetic field has changed and continues to change, not on a continuous basis, but from time to time, the magnetic North Pole will be down there where the penguins roam, and vice versa. And it happens, there is a frequency with which it happens, and it's a frequency in many tens of millions of years, but the magnetic field changes from north up top to north down at the bottom. And that's what they were able to find out. They were able to find that in the mid-oceanic ridges, such as runs right along the length of the North and South Atlantic, there were rifts, just the same as the Rift Valley in East Africa, and up the rifts, just the same as in East Africa, were coming volcanic surges. In the continental rifts, the volcanic eruption is from great big volcanoes like Kilimanjaro, like Mount Kenya, and a whole lot more. Not that they are active today, but they have been active. Those are volcanoes. And in the oceans, the lava comes up along these huge, long cracks which run the length of the mid-oceanic ridges. The mid-oceanic ridge is, or the mid-Atlantic ridge, runs from Iceland down pretty well to Antarctica, down the whole of the North and South Atlantic. And it's a huge mountain range, much higher than the Himalayas or the Andes, rising from the abyssal depths of the Atlantic up to not very far below the surface. In the middle, as I've said, are these faults which define the rift up which the volcanic material comes. The volcanic material, as it comes up, must make space. It pushes the sides of the rifts further and further apart, and that's what you see there, is that the north and south magnetic fields, which were changing and which can be measured, you can measure with instruments, and that's why technology has provided us with the motive force for continental drift. And this was one of the biggest breakthroughs. And this happened in the early 70s, and by the end, or by the mid-70s, the term plate tectonics was being used for the first time. Continental drift is still used. It's a more, in a way, it's a more descriptive term, continental drift, than plate tectonics, but the technologically correct word for the principle, and it's as much a principle in geology as evolution is in biology, the correct term is plate tectonics. And this is what happens. So you have plates which have, some plates are sliding under other plates, some plates are sliding over those, some plates are sliding along each other. So there are different types of plate margin. And where they move, they cause earthquakes. And in a lot of places, because of the subducting plate, which is the plate that's going down under another one, being carried into the very hot regions of the Earth's interior, rocks melt and granite, molten granite comes to the surface, which is what you see on the right hand, on the far right and left of the picture. Magma is the name given to molten rock. magma is what formed the granite at Paarl. It's what forms the volcanic rocks at the top of the Drakensberg. Those are all erupted and intruded as magma. We said that the movement of plates against each other is not a passive process. It happens with a lot of movement which registers as earthquakes. And this is what happens. It's in far western California. It's quite a recent one, 1989. And that's all, you probably all know the name of the fault that runs along western California. It's the San Andreas Fault. And that is what happens when the San Andreas Fault moves. South Africa is spared from that kind of movement, luckily. We don't have much by way of earthquakes at all here. We had the 1969 Ceres and Tulbach earthquakes. And that is the reflection, that is the manifestation of movement on very, very ancient faults, which were separating plates as Gondwana broke up. So we do have it, but very, very occasionally and in a very small scale. The division of the plates, African and South American plate, happens along the mid-oceanic ridge, the mid-Atlantic ridge, and the mid-Atlantic ridge is mostly under the water, but it comes to the surface in Iceland. And you'll all remember 2010 when air traffic in the whole of northwestern Europe was disturbed or interrupted completely for months on end, when there was massive activity on the mid-Atlantic ridge as it came to the surface in Iceland. So these are the effects of continental drift plate tectonics. We're not spared it. We've spoken about the mid-Atlantic ridge, but there are the same rifts that we spoke about. I spoke about Kilimanjaro and Kenya. This is in the Western Rift, the African Rift, which comes down from Ethiopia and kind of fizzles out north of South Africa, but is well represented in Central and East Africa. That's Nyiragongo, which is a volcano on the Western Rift, and it's been active recently, but its most active period was in 2002, and that's what it looked like at night. It's quite close to the town of Goma, which probably most of us have heard of, and it caused quite a lot of damage in Goma. The volcanic flows from the Nyiragongo volcano actually covered half of the Goma airport. Goma is a big, important capital town in eastern Congo, southeastern Congo. And that's not the airport, but that's through the town. And it gives you some idea of what happens when crustal plates move against each other or divide, and cause a lot of damage and loss of life. All right, so you've had to bear with me as I've spoken about the effects of continental drift and plate tectonics, which I was studying to try and get to the answer of whether, in fact, that was the explanation of what had divided the woodpecker population or the erythrina population. And I then studied the effects of plate tectonics as far as some of the more interesting maverick examples in plate tectonics. And one of those, by far the most extraordinary maverick example, is the little archipelago of the Falkland Islands. would seem, with the Falkland Islands, I'll just explain this slide. The AFFZ, which you see on the southern part of that map, is the Agulhas Falkland Fracture Zone. And now we all know where the Agulhas Bank is, we know where Cape Agulhas is, but you wouldn't expect the next word after Agulhas to be Falklands. But there it is. And it's called the Agulhas Falkland Fracture Zone because the microplate, which is called the Falkland Islands microplate, slid along that AFFZ from the Eastern Cape to where it now rests very close to the coast of Argentina, as Britain discovered.
So it really belongs to South Africa.
And it was a geologist from my alma mater, University of Natal, who, working in the Falkland Islands, recognized rocks that he knew well from eastern South Africa. And he said, he produced a map of the Falkland Islands, and he said, but the extraordinary thing is that the geology is the wrong way around. In other words, if the Falkland Islands microplate had drifted from eastern South Africa, as it drifted, inevitably, and it's not difficult to imagine, the friction along that AFFZ caused rotation of the plate, so that the rocks that are south in Falkland Islands now were originally north. And that's got nothing to do with magnetic reversal, it's just the rotation of the plate as it traveled from where it was, that's where it started. And if I were able to show it, it's just too much to show everything. That Falkland Sound, which opens to the north in this picture, actually opens to the south, but it's been rotated to have the geology in the right sequence compared to the South African orientation of the different rock units. Those are different rock units, as you can imagine, given the different ornaments, and they had to rotate them through 180 degrees to get them to match up with where they were. So now we come to the next part of the story. So that's where they moved from the Eastern Cape, that's where they are now. Darwin on the Beagle sailed across the Atlantic with Captain Fitzroy and the crew, and they traveled along the coast of South America, and they twice visited the Falkland Islands. And Darwin, first of all, studied the geology. Darwin was, amongst other things, was a geologist. He was a polymath. He made his name in biology, but in fact, he was just as interested in geology. And he spent quite some time on both visits in the Falkland Islands mapping the geology. And he was intrigued to find fossils that he knew from Britain. So there was a lot that he noticed about the geology of the Falklands, but what really attracted his attention was the fact that on the West Falklands and on the East Falklands, there were two different foxes. They were very similar, and unfortunately, if you go to the Falklands today, none of those foxes are still around. They've become extinct since Darwin was there. But he couldn't understand how it was that there were two populations of foxes that were slightly different, and as you saw from that previous map, the West and East Falklands are very close, but Darwin realized when he first visited the Falklands and then the Galapagos that archipelagos, and although it's only two islands, the Falklands is strictly speaking an archipelago, the Galapagos are a bunch of islands, 5 or 6, I can't remember, and he realized that his understanding of the multiplication of species was best illustrated in archipelagos. very similar to each other, but each one had a different beak. And each species that he identified as a species had a different beak. And he said, well, it's obvious they eat different foods, and their beaks are adapted to their food source. So Darwin observed the mockingbirds in Chile and then on the Galapagos, and he collected samples of all of these different finches. He hadn't started to formulate the idea of evolution by, what's it called, help me somewhere, natural selection. Evolution by natural selection. He in fact didn't even call it evolution, he called it the origin of species by natural selection. And he did that work together with other scientists in Britain when he got back from the Galapagos. On his way back from the Galapagos, he stopped in Cape Town, and this is a very much an aside, and I'm sorry I don't have pictures of it, but he went to a contact being what geologists call where two different rock types meet each other. He'd heard about a rather extraordinary contact in Sea Point in Cape Town, and he went to have a look at this. And at that stage, there was still great debate about the origin of granite. There was a great conflict between the Plutonists, who believed that granite originated from molten rock deep below the surface, and the Neptunists, who said, no, granite forms at the depths of the ocean. And Darwin saw the Sea Point contact, and if you haven't been there, I really encourage you to go there, because there's a good plaque up there saying what Darwin's discovery was, but it put the lid for once and for all on the debate about the origin of granite. And Darwin was the first Plutonist who could actually show from the Sea Point contact, guys, you can see this had to have been a molten rock intruding in a very hot state into pre-existing sedimentary rocks. So that was Darwin in Cape Town. But now we come to this whole question of long-distance dispersal. And I'm sorry, we are getting close to Arderne now. I'm sorry I've rambled on, but it's given you an idea of some geology which you may not have had before, and so I hope that has been interesting. But we now get to the alternative explanation. If it wasn't continental drift, and if you look at the birds and all of the animal life on Falkland Islands, you might think if it were vicarians, if it were that they had come from Africa, you might expect the creatures, the plants on the Falkland Islands to be African. They're not, they're South American, completely South American. So the answer appears not to have been entirely continental drift stroke plate tectonics. If it wasn't that, it has to have been the alternative, which is long distance dispersal. And the pictures I'll show now are examples of trees which we regard as African trees, or trees which may be regarded as South American trees, which occur widely across Australia, New Zealand, etc., etc. In other words, in Gondwana continents. Now, I'm sorry, the writing is probably not very legible on the top of that left-hand picture, but that is a Podocarpus. It's in Australia, it's indigenous, endemic in Australia. It has a variety of names in Australia, but the most common one is a plum pine. It's a yellowwood, but they call it a plum pine, which is fine. They probably find it odd that we call them yellowwoods. But you ask, why is it called a plum pine? That's what it looks like. That's what the cones, the fleshy part of the cones. And remember, these are all conifers. They're not flowering plants. resist showing that picture to show you what an Australian podocarpus looks like. Sorry. That's a Norfolk Island pine on the left, of which I think there are lots of representatives just a few meters from us here. And that's a picture of a monkey puzzle tree which I took in the Botanical Gardens in Edinburgh, Araucaria araucana. And it's a tree which is close to my heart, although I'm very much an African. But I have spent enough time in Chile to have seen that particular tree, the araucana, in its natural habitat, and it's a magnificent tree. And one of the reasons it's special to me is that it's named after the area in Chile, which is quite a small part of southern, not far south, but southern Chile, called Arauco. So that Araucaria araucana is absolutely endemic in the Arauco region of Chile. They occur widely in Cape Town. If you drive down some of the streets of Somerset West, you can see 3 or 4 different species of Araucaria. They're beautiful trees, and we have every reason to believe that they should be Gondwana trees. Paul, the Kari is a New Zealand tree, right?
Yeah,
And Queensland. Okay, so it's New Zealand, Australia. If you go to the Zico Museum, when you go to the Zico Museum, outside in the front is a reconstructed stem of a fossil Araucaria. It's in fact called Agaphoxylon, but it's an Araucaria. It's 230 million years old. Or the wood, the fossilized wood is 230 million years old. Now that's long before the continents drifted. It was an African Araucaria. We don't have them today, although your curator, botanist, Adam Harrower, is determined to find living species of living representatives of Araucarias in some hidden valley in the Eastern Cape. It would be an absolute breakthrough. And I hope Adam persists in his search. But as far as we know, the only representatives of Araucaria in Africa are that 230 million year old fossil. Now, it's difficult to read that, I'm sorry, but it was the best picture I could get. It shows you a list of all the Araucarias, and they're not all called Araucarias, some of them are called by different names, but they are all of the family Araucariaceae. And gosh, I'm sorry that it's so difficult to read, but the yellow bars are all from New Caledonia. The other bars are, a lot of them, from Pacific Islands, and a few from South America. There are one from Brazil, one from Argentina, and I think a couple from Australasia. So, one of the things that I think surprised Hank when we walked around the garden together and we spoke about Norfolk Island pines was that Norfolk Island is a volcanic island in the Pacific. A lot of those yellow bars, or not the yellow bars are all New Caledonia. New Caledonia is a chunk of Gondwana. But before the time of those Araucarias, the whole of New Caledonia was submerged below the Pacific Ocean. So you say, well, how did they get there? And the answer is absolutely incorporated in the term of long-distance dispersal. And long-distance dispersal also is sometimes known as sweepstake dispersal. And I think that's a delightful name because although we mostly think of lotto and other games of luck today by other names, the sweepstake is just as much a game of luck as anything. All right, so we move on in the field of long-distance dispersal, and we are going to look at some flowering plants. So far we've only looked at gymnosperms or conifers, and we look at flowering plants. Where are the flowering? Oh, it's difficult to see in this illustration, but flowering plants start quite recently. They start
there, in the middle on the left. You'll see the high pink.
Oh, thanks, Hank. Yeah.
There, up there.
Yeah. There we go. Thank you. So they make their appearance after the drifting of the continents. So they couldn't have been a pre-progenitor population that was divided. They must have been dispersed over quite long distances. I came across a paper doing my research in which an explanation was given of how tropical rainforest flowering plants had moved across the Atlantic. And you think to yourself, well, how can that be? This is a plot tree which is just up the road here. I took the picture about a month ago when it was in full flower. It's probably the biggest in Cape Town, if not biggest in the Cape. It's up near the M3, just where you come off the M3 to come down this way. It's in a garden, and it's a lovely, lovely specimen. You see good ones in Mpumalanga or at Nelspruit, which is more its home territory. But those trees came from South America. And nobody brought them from South America. They came by themselves. By other agencies. This is we don't see specimens like this in South Africa or in Africa, but that's a typical, well, probably not typical, it's probably an extremely good example of what they call Saber pentandra in South America. They grow to enormous sizes. They grow to enormous sizes in West Africa too. That's what they look like in the Amazon. They tower above the rest of the forest of the canopy in the Amazon. Magnificent trees. And they have these ferocious thorns, prickles they're called by botanists, up the stem. You would not dream of leaning against that tree or grabbing it with your hand to climb up into it. No way. They're amazing trees. These are some pictures I took in East Africa. And unfortunately, in Southern Africa, they don't produce fertile seeds. In East Africa they do, and it's certainly something to do with the pollination. And I spoke to Eugene Moll about this, and he produced an interesting paper for me about the fertilization by bats. And if we don't have the right kind of bats here, they're not going to get fertilized, they're not going to produce viable seeds, and we're not going to get fruit and product from the paper tree. But there is one in East Africa. problem with the fertilization there. This was a representation of the paper that I came across, and the writing on this picture is not mine, it's from the author. But if you remember the last picture that we saw, you'll remember the white fluffy kapok. And you can imagine how the winds would blow them across from northern South America into Africa. And that is proposed to be the way in which they got here. Wind for something as fluffy and light and airy as the kapok is all very well, but there are other explanations. This is from another paper that I came across, showing how ocean currents are also responsible for getting plants, flora and fauna across from one continent to another. And you say, well, most of these animals don't swim. How do they stay for weeks in the ocean? And the answer is, that's a picture of the Congo River. And there is a phenomenon known as near equatorial river plumes. And these river plumes, only near the equator, will go far out into the ocean, and only into the, mostly, in our case, into the Atlantic Ocean, because the world's two biggest rivers, as my good luck as somebody studying Africa and South America would have it, the world's two biggest rivers are by far the Amazon and then the Congo. So they come to the coast, carrying their water, but in flood times, they carry floating islands. And those are sections of bank broken off in the rivers, carried down to the mouth of the river and out by these near equatorial river plumes, way into the oceans, into the Atlantic Ocean, and into those conveyor belt-like systems that we saw in the last picture. Floating islands. So we're getting close to understanding how the birds, the woodpeckers, could have got around. That's a map showing the global distribution of woodpeckers. And interestingly, the green, which is in the bar at the bottom on the far left-hand side, unfortunately you don't see it on the far left-hand side, but the green is areas where there are no woodpeckers at all. The white is where there are very few woodpeckers, and then deepening shades of grey-brown are the more populous woodpecker populations. And what's interesting is I spoke earlier about the effect of the Andes as an item of vicariance, where population is barred from further progress by either an ocean or a mountain range. There is the Andes stopping the westward progression of woodpeckers. I came across in my research a paper about the cross-Atlantic mainly, but to an extent slightly, well, it really is cross-Atlantic, of Turdus thrushes. Thrushes, the most common thrushes go by the generic name Turdus. And they got from Europe into North Africa, from North Africa to South America, from South America back to Europe, and into North America. Ironically, the only representative Turdus in America is called, you'll never guess it, the American robin. It's a thrush. But, okay. So birds get across the ocean. The tourist thrushes got across the ocean. But having got across the ocean, they've got to go further. And an extraordinary story is how the good old African cattle egret, we like to think of them as, got to South America, got to northern South America. This map shows 1937. Other papers you read show an earlier first discovery. But don't forget, they have to get across as a breeding population. It's no good one bird getting there. So maybe the first bird got there in the late 1870s, but the first breeding population got to Guyana, the Caribbean, somewhere in 1937. But look how they've spread since then. So birds spread at a heck of a rate. They're by now, I think, up into Alaska and as far down to Patagonia as you can imagine. So birds move around.
Why so recent, relatively speaking, 37 to 91? There must be some other factor. That's a fairly recent.
You know, it's the sweepstake dispersal. It's the luck of the draw. And if their lucky number didn't come up before then, sorry. Now, there's a man called Arderne, who wrote a book called The Monkey's Voyage. Have any of you read The Monkey's Voyage? No, it's a pity. It's a wonderful book. I got a copy from Ernst van Jaarsveld, who got it from somebody in America, and I just loved the book. And I was able to get in touch with Arderne, the author of the book. And the climax of the book, really, was how apes and monkeys got to South America from Africa. And they got there on floating islands. Probably out of the Congo, maybe out of the Niger, one of the other African rivers, but they got from Africa to South America on floating islands. And if monkeys can do it, birds can do it, and plants can do it. Oh my God, I don't know what's happened there. But nothing much I can do about it now. But the conclusion that Arderne came up to was really the following. And it reflects and relates to my study of the woodpeckers and the erythrinas, which had assumed a continental drift origin and finally come around a long time later to an explanation by long-distance dispersal. And that's really what Arderne is saying. Vicariance is a priori a more probable explanation than dispersal needs, well, the assumption that vicariance is a more probable explanation needs to be re-evaluated and perhaps discarded. I don't think we can discard it. I don't agree with Arderne there because we cannot discard vicariance, i.e. continental drift plate tectonics, because look at that Agathoxylon fossil at the Zico Museum, 230 million years old in Africa. Then they got to South America, then they got to Australasia, and then, and only then, were they further distributed by long-distance dispersal or sweepstake dispersal, let's call it. That is an image that you're all familiar with, and that I'm not going to dwell on, but I think this is a lovely sentiment, and it's from your brochure, and I love it. And I really apologize profusely, belatedly, now that you've heard me, and you can chase me out now. I think the explanation that we have to give some thought to is what's described by biologists, biogeographers, as the overwriting of vicariance origins by long-distance dispersal origins. In other words, I don't agree with Arderne that we have to discard Presbyterian's continental drift, but I think we have to modify it. We have to overwrite it with the long-distance dispersal. And I would be very happy to be involved in such a project if it should ever come to it. And that is the end of my story.